today is a combined group, so we will continue with the lecture. Okay, then after that, only we in the next class only we settle the tutorial. Yeah. Okay, so now for the lecture today, we are going to look at the topic 2. Yeah, so topic 2 is just a very short topic. It's just one part of the lecture, 2 hours. Okay, it's all about the enzyme. Okay, so again, it is something that you have learned before. It's just that we will go more detail, especially on how to explain the graph. Okay, so now we will look at the learning outcome. So you can see the learning outcome. For some of it, you have learned it before. For example, properties of the enzyme, mode of action of the enzyme, the factor that affecting the enzyme. So all of these, yes, you have learned it before. It's just that maybe you didn't learn it that detail, okay, for the graph part. Yeah, for how to explain the graph and then what is the mechanism behind this. Yeah, maybe this one you didn't learn. Okay, so this is where we will focus more, right, in this lecture. Okay, so same thing, we will look at the learning outcome, the summary for the learning outcome. Okay, so for this lecture, right, we will basically look at 5 things, right? There are 5 small parts on that. Okay, so the first part, actually, we will look at the properties, right? The properties of the enzyme. So properties of the enzyme is just the fact. It's just some facts that you have learned before. So that's why I didn't list it down here. But, well, all of it is basically, it is specific, it is reusable, it won't be destroyed in the reactions of some of these properties. Okay, so if you want, yes, you can add on. Yeah, you can add on. Okay, but to me, well, it is just something that you just have to go through. Okay, so for example, when you look at the mind map, you see properties, right? So yeah, you tell yourself, what are the properties? Okay, just simply tell yourself 5 properties of the enzyme. Done. Okay, so done with this, then now next we move on to those that is more important. Okay, so the mechanism of action. Mechanism of action, you have learned it before as well. Okay, it is basically the lock and key hypothesis versus the induced fit hypothesis. Basically these two. Okay, so lock and key hypothesis, what is the most important point that you need to explain? Yeah, that you need to explain. Yeah, so whenever we ask you about the lock and key model, okay, so first one is, of course, you have to talk about the substrate and the active site. Their shape are exactly complementary, exactly the same. That's the first point. Okay, then second thing is, of course, rigid. The active site is always rigid. The active site will not change the shape at all. All right, that is for the lock and key hypothesis. Yeah, well, for the induced fit hypothesis, right, well, first one, the active site will have a slight change in order to feed the substrate better. Okay, so that's why you can see slight change. Okay, then second is flexible. Active site is flexible. Okay, that means they can change their shape, slightly change their shape. Okay, so based on this, this will be the point that is always important when you explain the mechanism. Okay, and same thing again. There are also questions that will ask you to compare. Yeah, compare. You can see here, compare. Okay, so to compare that, well, actually you don't have to memorize the new point, because to compare that, you can use back the same point, exactly the same point, in order to score for the marks. Okay, so that's why, yep, you don't have to waste your memory to memorize this and that. Just make it simple, make it general. Okay, so that is the part 2. Then next, part 3. Part 3, we will look at the factor affecting the rate of reaction, right? And this is something that you have learned it before. Okay, there are 4 factors that is going to affect the rate of reaction. So namely the enzyme concentration, substrate concentration, pH, and also the temperature. Okay, so normally, what you need to know is, first thing you need to know, what is the relationship. Okay, because whenever there is a factor, then the rate of reaction. Okay, so you need to know what's the relationship between the factor and also the rate of the reaction. So that's the first thing that you need to know. Okay, and then second thing, you need to know how to explain the graph, because you look at the graph, and I think in secondary school you have learned some graphs like this. Okay, it's just that maybe some of the teacher will teach you, they have taught you that yes, how to explain this graph, but some of the students no. yep, this is the second thing that you will look at. And in the mind map, you can see here, you can see there's a number 1, 2, 3. This is actually the step for us to explain the graph. Yeah, it's actually how we explain the graph, because this is how our marking scheme will look at in general, basically. Okay, so we can see normally we will explain for the graph of enzyme concentration, we will explain in 3 parts. So the first part is when the enzyme concentration is very low. Part number 2 is when the enzyme concentration is increasing, mainly from here to here. Okay, and then for part 3, this is when the graph level off. So normally we will explain in these 3 sentences. Okay, so you need to know how to explain these 3 parts. Then only then you can score the 3 marks to 4 marks. Yeah. All right. So over here you can see I put 1, 2, 3. So this is the 3 points. So when you look at the mind map, so you will know that okay, first one I need to explain this. Second I need to explain this. Third one I need to explain this. Okay. So how you explain these 3 parts? You need to explain it based on in terms of active site. You need to explain in terms of active site. Okay. For substrate concentration, same thing, 3 parts. Okay. How are you going to explain it? Same thing. You will explain it in terms of active site as well. All right. Then for the pH graph, well, there will be part 1, part 2, and part 3. So for part 1 and part 3, you will explain in terms of denaturation. For part 2, you will explain in terms of optimum temperature. Optimum pH for this one. Okay. Then for temperature graph, there will be part 1, part 2, part 3 as well. Part 1, you will explain in terms of kinetic energy. Part 2, you are in optimum temperature. And then part 3 in terms of denaturation. This is how you explain it in general. Okay. So I make it simple like this. Okay. I make it very straightforward, simple like this, step by step, because quite a lot of the students, when they go into the exam, they don't know how to explain that. Okay, so that's why I make it simple like this. So you just follow these 3 steps, then definitely you will be able to explain that. Okay, so no matter how the question twists, you will for sure able to explain that. Yeah. So now the key is what? The key is you need to know what is the reason behind this. That only then you can explain that. Yeah. So that's why later in the lecture, yep, I'm going to describe further because maybe you don't know what it means by explain in terms of the active site. Okay, so yeah, later we will talk about it. Yeah, so yep, you can jot down later if you want. All right, then that is basically for the graph. Yeah, for all the factor graph. Yeah, so there are total 4. Yeah, there are total 4. Okay, so and this is the second thing, and then the third thing would be the limiting factor. The limiting factor in the graph. Yeah, the limiting factor in the graph. Okay, so that will mean that later when we explain in the lecture, okay, we are going to look at 3 things. First thing is we will look at the relationship. Second, we will look at how to explain the graph. And then the third thing is we will look at the limiting factor. So these are the 3 things. Okay. Then next, enzyme cofactor. This is the part 4. Okay. So the subtopic 4, enzyme cofactor. So enzyme cofactor, we are going to learn 3. Enzyme activator, coenzyme, and also prosthetic group. Okay, so what you need to know about them, and what you need to know about them. Okay, so first one, you need to know whether they are organic or inorganic. All right. Then second, you need to know whether they bind temporarily or they bind permanently to the enzyme. All right, and then lastly is where they bind to the enzyme, in order to work. Okay. Then, of course, in the lecture later, I'm going to give you some of the examples, some of the real life examples to help you to understand, understand the how these cofactor actually work, how actually these cofactor allow the enzyme to work properly later. Okay. So again, that example, that real life example that I give you, is not a must to memorize, yeah, okay, because that is just an exposure in case higher order thinking questions, level 4 question come out with a real life example, at least you know how to apply that. Okay. All right, then that would be the part 4. Then part 5. Okay, part 5, it would be on the inhibitors. Yeah, on the inhibitors. So for the inhibitor, there will be competitive inhibitor and non-competitive inhibitor. Okay, of course, there are also reversible and also irreversible inhibitor. There are two categories in the node. Okay, but sometimes that makes some confusion. Yeah, that makes some confusion. Okay, so that's why I didn't further categorize it, but then I just tell you that under the competitive inhibitor, most of the time they are reversible at the same time. Okay, for non-competitive inhibitor, most of the time they are irreversible, but there are chances that these non-competitive inhibitor are reversible inhibitor at the same time. Okay, so with that, hopefully that will reduce your confusion on that. Okay, because sometimes you will thought that some students they will thought that competitive must be reversible, non-competitive must be irreversible, because in the note you can see they categorize by what? They categorize by reversible, irreversible, competitive, non-competitive. Okay, but can the non-competitive be reversible? Actually, it's yes. Right? Actually, it's yes. Okay, so this is the point where a lot of students actually confuse it. Okay, so that's why don't waste this easy mark. If let's say it come out, make sure you score. Okay, so next we go back to the competitive inhibitor. Yeah, competitive inhibitor. First one is yes, how they bind. Is it binding temporarily or is it binding permanently? Okay, so you can see here. All right. Well, for non-competitive inhibitor, they can bind permanent, they can bind temporarily. Why? Because if they bind permanently, then the reaction is irreversible. That means that it will be irreversible inhibition. Okay. If let's say they bind temporarily, then they will be reversible. So that's how it works. Yeah. Then next, where they bind. Yeah, where they bind. One is binding to the active site, and another one is binding to the allostatic site. So all of these points listed is actually the point that a very general point that always come out in the marking scheme. So that's why you can always use this point if let's say they ask you to compare. If they ask you to compare the non-competitive and competitive inhibitor, these are the points that you can use. Okay, if let's say they ask you to compare the cofactor, or if they ask you to compare the, for example, they can ask you to compare coenzyme and also the competitive inhibitor. So how are you going to compare that? Okay, so these are all the general points that you can compare actually. All right. Then lastly, under the inhibitor, there are two graphs that you need to know. Yeah, there are two graphs that you need to know. Okay, so you need to know how the inhibitor graph will be changed. The red line is normal without any inhibitor. Okay, then when you add the competitive inhibitor, how the graph will change? The graph will change like this. Okay, and if let's say you add the non-competitive, it will change like this. All right, so as for now, you just accept that first. Well, adding the competitive inhibitor is going to increase the Km, and the Vmax will remain the same. That means no changes. Okay. Well, for the non-competitive inhibitor, they will remain the same Km but lower down the Vmax. As for now, you just accept that this one first. But later, after the lecture, when you look at it, that only you will understand it. Okay. Then after that, after you know about the graph, then one last thing is that when there's a combined graph, that means that when there's a reaction with the competitive inhibitor compared with the reaction with non-competitive inhibitor, and at the same time compare with the normal reaction without any inhibitor. Then there are three lines of the graph. How are you going to identify? How are you going to explain that? Okay. So for this one, well, if let's say you feel confused, this is basically what we can explain. How you can explain that? You just follow that only. Okay. So for identification, well, you will see the competitive inhibitor graph, right, is always having the same Vmax with the normal one, while the non-competitive is always having the same Km. Okay, well, Vmax, non-competitive inhibitor, right, they will lower down the Vmax. Okay, well, Km and half Vmax, right, competitive inhibitor, they will always have same half Vmax, increase Km, while non-competitive is always having lower half Vmax, but then same Km. So all of these are the relationship. All right, so as for now, again, it means nothing to you, right? So you just jot it down first. You can later on, when you go back, okay, you can refer back to the recording, and then you can jot it down somewhere. Okay, so these are the point that will help you to explain the graph when it's a combined graph, and also to compare the graph, okay, and also yeah, to identify different graphs. So that is how it works, okay. But all of these, yes, we will go through in detail, right, in the lecture. All right. So with that, yeah, that would be all the important learning outcome today. So let's see. So yeah, there are total 5. Yeah. So let's see the first one, the properties. All right. So the first part of the lecture is on the properties. Yeah, the properties. So properties, I think, is very simple. All right. So the first one, well, enzyme. What is enzyme? Enzyme is actually a biological catalyst. Yeah. It's not so right to say it is a catalyst only. Okay, why? Because catalyst can be, a chemical catalyst. All right. So enzyme is biological. Yeah, it's biological catalyst because it's an organic compound, right? That occurs in the living organism. Yep. So that's why it's biological, and it's catalyst because it speed up. Yeah, they speed up the rate of reaction. Okay, and in fact, all the organisms are able to survive mainly because we have the enzyme. Because if without the enzyme, the reaction will be so slow and it won't be able to meet our metabolic needs, and we will be dead. All right, so that's why we need the enzyme. Yeah, any denaturation in the enzyme will means that it is going to cause the cell death, and when there's too much of the cell death, will means that the organism will be dead as well. Okay, so that's why enzyme is so important for the living organism to stay alive, to survive. Okay. All right, then next, of course, the enzyme will have their specificity. They are well known for their specificity. Okay, they are very specific. Okay, mainly because why? Mainly because their active site is very specific to the substrate. They don't just like bind to any simple substrate. No, they are specific, very specific. Yeah. All right, then of course they need an optimum condition. They will need optimum temperature. They will need optimum pH in order to catalyze the reaction at the maximum rate of reaction. Okay, so that are the 3 properties of the enzyme. Yeah, so there are lots more. Okay, so enzyme, I think this one I have mentioned this during the protein, right? In the protein lecture, all the enzyme must be a tertiary structure. It must be a tertiary structure. Okay, at least, yeah, because in order to be functional, it must be at least a tertiary structure. So most of the enzymes, they are tertiary structure. Right? Most of them, they are tertiary structure, okay? And of course, they are quaternary structure enzyme. Yes, there is, okay? And all of these enzymes cannot be fibrous protein. They must be the globular protein. Because when they are globular, only they will have a shape, okay? Only then they will have a 3D shape like this. Then only then they can have the active site. Yeah? So that's why that is the structure, right? So when the enzyme, right, folded in the tertiary structure and having the active site. So what would be at the active site? Yeah, the active site, right? So for example, I said this is the active site, right? Okay. So why the active site is so specific? Actually, it's not just the shape. Yeah, it's not just the shape. Okay. That also include what? Because that will mean that all the amino acid that lining the active site, right? Their R group will be free. Their R group will be facing here. Okay. So all of these R group is mainly to do what? It's mainly to form the bonding with the substrate. Yeah, to form the bonding with the substrate. So that will make it so specific. Okay, because it's not just the shape only, It's not just the shape, but also when the substrate come in, it need to be able to form the bonding with all of these side chain. That only then they will be fit in. Okay, so that's why they are so specific. Okay, so that's why if let's say you change some shape here, change the shape there, okay, or you change the sequence here, then the protein, the enzyme will be losing their function. That is why it becomes the denaturation. Okay, so enzyme is even more sensitive on that. Okay, right. So these are more properties. Yeah, more properties. Okay, so first one, highly specific, as I mentioned just now, not just the shape and also the bonding as well. Okay, then second, they are highly efficient. They are highly efficient. Yeah, okay, meaning that they are having a very high turnover number. High turnover number will means that turnover number will means that how many molecule of this product can be produced from the reactant, okay, by one molecule of the enzyme per unit of time. Okay, normally, yeah, for some of the enzyme like catalase, they are having 600,000. Their turnover number is 600,000. 600,000 will means that in 1 second, one molecule of the enzyme, this catalase enzyme, is able to catalyze the production of the 600,000 product. So you can imagine how fast is that. Okay, so because the enzyme can work so fast, they are super efficient. Okay, and that's why we not really need a big number of the enzyme on that. Concentration of enzyme when it's low, so it's like, I think I shouldn't say like this. Okay, we only need a small amount of the enzyme. Okay, we only need a small amount of the enzyme in order to achieve the highest rate of the reaction. Okay, because they are highly efficient. Okay, so then next, they are reversible. Usually, they are reversible. Most of the reaction that catalyzed by the enzyme, they are reversible. But of course, there are some that's not reversible, but most of the time it's reversible. Okay, example like what we have learned before. Okay, if you still remember the H2O plus the CO2, and then it becomes the H2CO3. Okay, so the reaction is not just one way; it will be two way. Right, it will be two way. Most of the reaction in our body are all two ways. Okay. All right, then next, the enzyme will remain unchanged. It will remain unchanged. So that actually, it also means what, it also means that the enzyme actually don't involve in the reaction. They don't involve in the reaction. They just serve there, okay, as a platform for the enzyme, for the substrate to work well, okay, to meet better so that they have higher chance to form the product. That is what the enzyme do. Okay, enzyme don't involve in the reaction. Yeah, they don't involve in the reaction. Okay, they are just serving there only. Okay, so that's why they will still remain unchanged. They are reusable. Yeah, they are reusable for the next reaction and next reaction and next reaction. So that's why we only need a small amount of the enzyme. We don't need that much. Okay. Then yes, they need optimum temperature and pH, and they will be denatured if, let's say, they don't meet the optimum pH or the temperature. Okay, so that would be all the properties of the enzyme. Okay, so yep, that's just the simple properties. And then next we will look at the mechanism of action. Yeah, mechanism of action. So for mechanism of action, there are two. There are two hypotheses. One is the lock and key hypothesis, and another one is the induced fit hypothesis. Okay, there are two. Okay, so first one is actually Imao Fisher. Imao Fisher come up with the first model first, which is lock and key model first. Okay, he come up with this one first. So under his hypothesis, he actually proposed that the enzyme, right? Yeah, the enzyme, right? And also the enzyme and also the substrate must be having exactly complementary shape. Their shape must be exactly the same. Then only then they can bind. Because according to Imao Fisher, he said that the specificity of the enzyme is due to their shape. It's totally due to the shape. Okay, so that's why they are specific, because their shape is must be exactly the same. Okay, so when they are exactly the same, means what? Means that the active site is totally rigid. It won't change the shape at all. If they change the shape, means that the enzyme is denatured already. This is what Imao Fisher said. This is what he proposed. Okay, because during his time, this is like 100 years ago, more than 100 years ago. Okay, so when he come up with proposed this hypothesis, okay, the enzyme that he know, not much. Yeah, not much enzyme that he know. Okay, so what he can see is that most of the enzyme is actually specific, one to one. one enzyme, one substrate only. Okay, so that's why he proposed this lock and key model. Okay, so that is the two most important points in his hypothesis. Okay, so because of this, so that will means that the enzyme is like the lock, and then the substrate is like the key. It must be fitting in properly, exactly fitting in, and then only then they can catalyze the reaction. Okay, so that's the lock and key model. Okay, so yeah, that's why substrate is like a key, enzyme is like a lock. All right, but the problem is that, well, as the advancement of the technology, you will find out that there are actually quite a lot of the enzymes that does not follow this lock and key model. Okay, there are some enzymes that are actually not following that. Okay, because according to the lock and key model, one enzyme can only recognize one substrate only. Okay, but in fact, there are enzymes that can recognize two, and some even three. Okay, for example, the fatty acid amide hydrolase. These enzymes, they can actually bind to fatty acid. They can also bind to the amide. So lock and key model, for sure, it will fail to explain this. How come one enzyme can bind to two substrates? Two different substrates. One is fatty acid, one is amide. Okay, so how come? So definitely there are some, some arrangement or some modification in the enzyme. Okay, so that's why Koslen, Dr. Koslen actually come up with the second hypothesis. So this second hypothesis is actually a modified version, enhanced version of the lock and key. Okay, lock and key is suitable for most of the enzymes, but some of the enzymes they fail to explain that. So that's why induced fit hypothesis try to explain that phenomenon. Okay, so what the induced fit hypothesis actually state? Okay, so first thing is that the shape, okay, the shape of this active site is not exactly the same like the substrate. It's not exactly the same. Okay, the shape is like almost similar candy. No need to be exactly complementary. It's just like almost similar, then it's fine. Okay, why? Because when the shape is almost similar, then it enables the substrate to bind to it. So when the substrate binds to the active site, okay, so it is going to stimulate the conformational change of the enzyme. It's going to cause a conformational change, a slight conformational change, a small changes. So these small changes is going to now change the shape of the active site to make the active site perfectly fit with the substrate. Okay, then only then the enzyme will catalyze the reaction. Then only then the product is being formed. Okay, so there's a small changes here. That means that it's not the active site is no longer rigid. They can slightly change a shape, slightly change only, not a big change, just slightly change. Okay, so it is the substrate bind to the active site, cause the conformational change of the enzyme structure, and thus cause the active site to now change a bit to perfectly fit the shape of the substrate. Then only then they catalyze the reaction. That's how it works. That's the induced fit. Okay, so that is the mechanism. Yeah? Okay, so far induced fit, right? They can actually explain why some of the enzymes they can have greater range of the substrate specificity, and that's why this model is actually more widely accepted now. Okay, so this would be the two mechanisms of action. Right. So with that, yes, simple. Okay. So now the last part for the mechanism of action, how the enzyme actually works. Yeah, how the enzyme actually works. First thing first, enzymes don't involve in the reaction itself. They don't involve. Okay. So then how the enzyme can actually speed up the rate of reaction? How? Well, the key is because they can lower down the activation energy. They will lower down the activation energy. Okay. So, well, in nature, the reactant yeah, the reactant will always having higher energy than the product. So you can see that reactant will have higher energy for the product. So that's why the reaction will favor this direction. So that's why the reactant can form the product in nature. Okay, because reactant higher energy, product lower energy. So by nature, they will favor in this direction. Okay, because if not, then it will be product to reactant already. Then this one is no longer called product, it's called reactant already. This one becomes product. Okay, so that's why it's impossible that product having higher energy than the reactant in nature. Okay, because if that, then it will be going the different direction. Okay, in chemistry, different now. Chemistry, because you add energy to that. So that's why anything can happen. Okay, but for here, in nature, for most of the reaction that catalyzed by the enzyme is basically reactant having higher energy level, product having lower energy level. Okay, so by nature, the reactant will tend to hit each other and then become the product. But then not all the reactants can just simply become the product. Okay, why? Because they need to cross a barrier. They need to cross the energy barrier, then only then they become the product. That means that this reactant, when they hit each other, they need to reach certain level of energy. They need to hit certain level of energy or higher than this, then only then they can become the product. So that's the energy barrier. And this energy barrier we call it activation energy. Okay, so all the reactant molecules, they are basically randomly moving. Yeah, they basically randomly moving. Okay, so when they hit each other, okay, well, maybe I would say 100% of the molecule, right? Okay, maybe 20% is able to hit this energy. When they hit at this energy. Maybe they hit not at the right angle. So that's why the energy level when they hit is just maybe reaching here only. Another 20% maybe they hit harder. They hit harder. Okay, so they will reach this energy. This is another 20%. Okay, then another 20% they hit better. So they will be here. They will reach this energy level. Okay, then maybe another 20% they hit harder, stronger. Okay, so it will be another 20% here, maybe another 20% here. Reach this energy level. Okay, so in this case, without the enzyme, only which one will be able to form the product? Only this 20%. Because they reach this energy, means that they cross the energy barrier. So that means that 100%, only 20% will be able to form the product. So the rate of reaction is basically the number of the product that's being formed over the time, over unit of time. Okay, so with lower number of the substrate able to form the product means what? Means that lower rate of reaction. So what the enzyme will do is that they will lower down the activation energy to here. When they lower down the activation energy to here, so that means that how many percent of this reactant can become the product then? It will mean that 60%. Okay, with the enzyme, it will now lower down the activation energy to here. So when it lower down the activation energy, so this 20%, this 20%, this 20%, total 60% of the molecule can now pass the energy barrier and then form the product. So with that, they increase the number of the product over the time. So with that, it increases the rate of reaction. So that's how the enzyme actually works. They lower down the activation energy so that more reactant can actually achieve or pass through the energy barrier in order to form the product. So that's how they increase the rate of reaction. Okay, clear about this? This is how the enzyme works. Yeah? They don't involve in the reaction. Right? What they do is they just lower down the activation energy. Okay. Right then, next we will look at the part 3. Yeah, the subtopic number 3. Subtopic number 3 is we will look at the 4 factors. Yeah, the 4 factors. Okay, and that is basically yes the major part that we will look at. Yeah, the major part. Okay, then another major part is the inhibitor. Yeah, the graph. Yeah. Okay, so now we will look at the 4 factors here. Okay, so the first factor, we will look at the enzyme concentration first. Yeah, enzyme concentration. All right, so now first thing first, first factor, the graph looks like this. Yeah, the graph looks like this. Yeah? Okay, so for the enzyme concentration, uh, when we explain, we will look at three things. Yeah? We will look at three things. First thing, we will look at what is the relationship between the factor and also the rate of reaction. Okay. Second, we will look at how to explain the graph. Okay. And then third one, we will look at the limiting factor. How to explain the limiting factor. Yeah. Okay. So now we look at the first one, enzyme concentration. Yeah. So what is the relationship between the factor and also the rate of reaction? So for enzyme concentration, the relationship is directly proportional. Directly proportional means that the higher the enzyme concentration, the higher the rate of reaction. It will increasing. Okay. So in theory, the graph should be keep on increasing. In theory, it should be just increasing only. It shouldn't level off. Yeah. In theory, it shouldn't level off. Okay. So that's a relationship. It is directly proportional. As long as you increase the enzyme concentration, it is going to increase the rate of reaction. That is their relationship. Okay. Then how come it level off? Later we will talk about that. Yeah. Okay. So next, how to explain the graph? So to explain the graph, we will explain the graph in three parts. We will explain the graph when the factor is low. We will explain the graph when the factor is increasing. This part. Okay. And then we will explain the graph when it level off. Okay, three parts of the graph. Okay, so now for the first part, when the enzyme concentration is low, when the enzyme concentration is low. So I think it's over here. Yeah, enzyme concentration is low. This is first part. This is how they explain that. When enzyme concentration is low, the rate of reaction is also low. Why? Because the number of the active site is limited. Okay, the number of the active site is limited, so that's why there's high competition between the substrate for the active site. Okay, low active site, high competition. Right, so that's why the rate of reaction is low, or you can say that's why not much enzyme substrate complex can be formed. Okay, so that's the first part. That's the part one. Okay, then next, part two of the graph. Part two of the graph, as the enzyme concentration increase, the rate of reaction will also increase. Okay, so why? Because when the enzyme concentration increase, that will mean that more active site available for the substrate to bind to. And that will mean what? That will mean that more enzyme substrate complex can be formed and thus increase in the production of the product over time. Okay, that is point number two. Okay. All right, then next. Point number three. Yeah, point number three. Okay. Point number three is as you increase the enzyme concentration beyond some point, beyond certain point of the graph, okay, further increase in the, or you can say starting at certain point of the graph, okay, further increase in the enzyme concentration will no longer increase the rate of reaction. Okay, further increase in the enzyme concentration will no longer increase the rate of reaction. What's the reason? Because, right, there is not enough substrate to further push the rate of reaction up. Okay, or you can say because the concentration of the substrate, okay, is a limiting factor. Okay, the concentration of the substrate becomes the limiting factor. Okay, so causing the rate of reaction not able to further go up. right? So that is basically how I explain for the three part of the graph, right? So actually, all the point is here, yeah. Actually, it's here. It's just that you know, maybe it's maybe a bit incomplete, okay? But if you want, yeah, you can use my point. Okay, so that is how you explain three things. So you can see all of it is talking about what? All of this is talking about the active site. It's all explained in terms of the active site. Okay, so that would be the enzyme concentration. Yeah. Oh yeah. Then lastly, talking about the limiting factor. Yeah, talking about limiting factor. Yeah. So for this graph, yeah, for this graph, if let's say the question asks you to identify the limiting factor at different part of the graph, yeah, okay, then the whole graph can be separated into two. Okay, the graph that is still following the directly proportional relationship and the graph that is level off. Yeah. Okay. So yeah, for this part, right? This part you can say the graph level off, or you can say the graph reach the asymptote. Either one. You can say the graph level off, or you can say the graph reach the asymptote. Okay. So basically, if let's say the question asks you for limiting factor, for example, they ask you, what is the limiting factor at this point? What is the limiting factor at this point? Okay, at point A, yeah, that means actually the whole line here, yeah, the whole line here, any point, they ask you what is the limiting factor. Okay, the limiting factor, look into the x-axis. That is the limiting factor. When the graph is still directly proportional, it's still going up, okay, any limiting factor, that is the limiting factor, enzyme concentration. Look at the x-axis. Okay, but then when the graph level off, if the graph level off, then that means that if let's say this is enzyme concentration, then the limiting factor will be the substrate concentration. Okay, yeah. So that's basically the three things that we need to discuss. Okay. All right. Then next one, yeah, for this one. Okay, this one is the same thing. You further increase, then it will increase very fast. Okay, this one is actually they want to talk about the rate of reaction. Yeah, they want to talk about the rate of reaction. Okay, so now for this slide, this additional slide, right? This one is to actually answer one of the past year questions that has come out before. Actually, they asked, yeah, how come when we are increasing the rate of reaction, right? Okay, at the beginning, you see the slope, right? You can see the slope, okay? The slope is very high, okay? But then as it want to level off, it will slow down, okay? So how come? So this is one of the past year they asked before. Because how come it will slowly become slower and slower? Yeah, slowly it will become, you can see the slope is different. Okay, so they are asking why. Okay, why before level off it will become like this? Yeah. Okay, so this one all because of what? Because the concentration of the substrate has become lesser. Right. The reason why it will slow down like this, right, is because the concentration of the substrate level, right, the concentration of the substrate has become lesser, has become lower. Okay. So when the concentration of the substrate becomes lower, they are still able to, to maintain certain high level of the rate of reaction. They are still able to, okay, but they are no longer able to be very fast at it. Why? Because lower concentration, but all of this rate of reaction, it totally depends on what? Rate of reaction totally depends on the production of product, right? So the production of product, it depends on what? It depends on the reactant enzyme substrate, okay, there are a lot of the substrate. Let's say 1 million of the substrate, okay. So you have enzyme like this. Enzyme, this is an enzyme, okay. At the very beginning, at the very beginning, when enzyme is low, okay, there are a lot of substrate. Let me copy this. Cannot draw all. Draw all, then it become end of class already. Okay. You can see at the beginning. This is at the beginning. Yeah, very little enzyme, right? But then there's a lot of substrate. So the chances of this substrate to bind with the enzyme high or low? The chances, in the Brownian motion, the chances when they move, randomly, you have so many substrates. The chances for the substrate to bind with the enzyme high or low? Extremely high. Okay, so over time, you keep on increasing the enzyme concentration. You keep on increasing the enzyme concentration. Okay, but at the same time, you are using up the substrate because all of these substrate, let's say, finish up already, right? Okay, so maybe at this point, this is the only substrate left. All of these used up already. Okay, although you have increased the concentration of enzyme, but substrate level is lower now, right? So what is the chances for this substrate to hit the enzyme? Will it be higher or lower? Of course, it's lower. Okay, even though you increase the enzyme already, but then substrate level also become lower already, right? So that's why the chances to hit the enzyme is lower now. So because of this, so that's why the graph, right? The slope that will be less slanting. Okay, so that's the reason. Okay, or you can say the slope is decreasing. Okay, so that's the reason, because the concentration of the substrate has actually decreased, and that will mean that will decrease the chance for the substrate to bind to the enzyme. Okay, that's how we explain. So before this, because this is actually higher order thinking question, but then a lot of students say they totally don't know how to answer it. So that's why we add in this slide. Okay, so to further explain that, yeah. Okay, and okay, that lastly, for this one, this slide there is something wrong here. Okay, reaction don't stop here. Yeah? Reaction don't stop here, unless I think maybe because when they prepare the slide, they use the wrong graph. Unless the y-axis, if the y-axis is the concentration of the product, if the y-axis is concentration of the product, not the rate of reaction, then yes, reaction stop. Because you see concentration of the product, right? It increase until a certain point, it level off. Means what? Means that the concentration of the product no longer increasing. And then yes, reaction stop. Okay, then the whole explanation can be used here. Okay, remember, this is also one of the higher order thinking questions before this. Okay, analysis. So in exam, sometime be careful on this. Okay, the graph not necessarily must be the rate of reaction here. Okay, please be careful. It can be concentration of the product. Okay, so if let's say it is a rate of reaction, then the reaction still ongoing. Okay, even when the graph level off, even when the graph level off, okay, if let's say over here is a rate of reaction, means that the reaction still ongoing. Okay, but if let's say it is a concentration of the product, that means that the reaction stopped already. Okay, so that is the meaning there. So you have to remember that. Okay, be careful on this, because sometimes the questions, when they use the graph, they will put either rate of reaction or concentration of product. Okay. Okay, then next we will look at the second factor. The second graph factor. So this one is the substrate concentration. Substrate concentration. This is second factor. graph for the substrate concentration is same like the enzyme concentration. It is the same. Okay. So now, what is the relationship? Same relationship, directly proportional. Yeah, directly proportional. So means that as long as you increase the substrate concentration, it is going to increase the rate of reaction. Okay. So next, how we explain the graph? Yeah, how we explain the graph. So the way that we explain the graph is the same, like the enzyme concentration. It's just that you have to be careful. A lot of students confuse here. Okay. Now, what is the factor? The factor is substrate concentration. Yeah. Okay. A lot of students, when they see the graph, they are so happy. Everything also they explain in enzyme concentration. That would be wrong. Okay. Don't waste this mark again. Yeah. So this one. Yep, substrate concentration, same thing you explained in the first part, when the substrate concentration is low, when the substrate concentration is increasing, when the graph level off. Three part also. 1, 2, 3. Okay, so same thing now. Let's see. At the low substrate concentration, yeah, at the low substrate concentration, okay, so there are a lot of the active site that is not occupied. At low substrate concentration, the rate of reaction is low because there are still a lot of the active sites that are not occupied. You can say that there are still a lot of the active site that is unused, or there are still a lot of the active site that are still empty. Okay. So that's why there's very little product being produced over time. Okay. Then next, second, part 2. Okay, part 2. As we increase the substrate concentration, the rate of reaction also increase. And the rate of reaction also increase. Okay, why? Because now more substrate can bind to the active site and form the enzyme substrate concentrate. Form the enzyme substrate complex. Okay, and because of this, more product can be produced over time and thus increase the rate of reaction. Right? And then point number 3, level off. When the graph level off, or when the graph reach the asymptote. Okay? So when the graph reach the asymptote, means that beyond this point, you further increase the substrate concentration, the rate of reaction will be same. Right? It will be stagnant. Okay? So what's the reason? Well, the reason is because now the enzyme concentration has become the limiting factor. Okay? Or you can say that all the active site of the enzyme are now saturated. All the active site of the enzyme are now saturated. So that's why you further increase the substrate. There's no more active site that's available. All the active sites are saturated. So that's why the number of the product that can be produced over time will remain the same. Okay, so you see the difference? In enzyme concentration, okay, you will say that there's not enough substrate concentration. Okay, and in the enzyme concentration, in the substrate level concentration graph, we will say that because the active site becomes saturated already. All the active site of the enzyme are saturated now. So that's why they are not able to further increase the number of the product that can be produced over time. Okay, so that is basically how we explain. Yeah. So I think it's all here lah. Yeah, it is basically all explained here. If you want, you can memorize from here also. But for me, my advice is don't memorize it. Okay, understand it and then write with your own answer. That would be better. That would be easier. Okay, because when the question becomes analyzing or become application type, well, that is where you need to answer based on the understanding. Okay, so that would be the 3 parts. Yeah, 1, 2, 3. Okay, then last one. What is the limiting factor? And what is the limiting factor? Same thing. Yeah, the graph I look at here. Same thing. What is the limiting factor here? All the point here, all the limiting factor at any of the point here, it will be substrate concentration. And any other point after level of the limiting factor will be enzyme concentration. Okay, yeah? All right, so that would be substrate concentration. Then next. Okay, next is the pH, the graph of the pH, yeah? Graph of pH. So for the graph of pH, yeah, for relationship, yeah, for the relationship, well, the relationship very simple. Relationship is related to optimum pH. Yeah, it's related to optimum pH. Okay. So what is the relationship? The further the pH change from the optimum pH, you cannot say lower or higher only, because some students will say the higher the pH, the lower the rate of reaction. That would be wrong. Okay, because different enzymes have different pH. Different enzymes have different optimum pH. Okay, so for example, like the pepsin enzyme, pH 2, that is the optimum. Okay, for example, like trypsin, their pH is pH 8, optimum. So that's why you cannot say, oh, that's a lower than pH 7, higher than pH 7. No, amylase, they are pH 7. So that's why different enzyme, different pH. So this is one of the key that you need to remember. Okay, you cannot say the higher the pH, the lower the rate of reaction. No, you cannot say like this. You have to say that the relationship is the bigger changes from the optimum pH, okay, the lower the rate of reaction will be. It totally depends on optimum pH. So that's their relationship. Okay, and then I need to highlight one thing here. Yeah, this one please remember. Yeah, the graph. For example, during the MCQ, for example, okay, they will give you different graph A, B, C, D. Okay, then they ask you to choose which one is the graph for the pH. Okay, so sometimes they will give you almost the same. For example, they will give you something like this: A, B. Then some students, they didn't know which one I should choose. Which one is the graph for the pH? They will also give one more. C. So based on the shape of the graph, can you know which one is the pH graph? So please remember, for pH graph, it is always a narrow bell-shaped curve. A very narrow one. Okay, both sides also narrow, yeah? Both sides also narrow. Because like C is like one side narrow, one side not so narrow. Okay, so please remember, it should be very narrow. Okay, because the enzyme, right, their pH, right, they cannot actually having any reaction, okay, as long as the pH different from the optimal pH is more than 1. So for example, this one, pH 7, right, pH 7, okay, you see within at 6, the pH, the rate of reaction becomes so low already. Okay, so that's why the graph is very narrow. Why? What is the reason behind this? This is another question that can be asked. Okay, so the graph of the pH will be very narrow like this. Okay, that will mean that just a small changes in the pH is going to cause a very drastic decrease in the rate of reaction. Please remember, when you describe it, drastic decrease or drastic drop. Okay, why? What's the reason? Because the enzyme is super duper sensitive to the change of pH. Yeah, because the enzyme is super duper sensitive to the pH changes. Okay, so that's how we explain that. Yeah, 1 mark. Yeah. Okay. Yeah, so if it come out, then you all will be very happy then. Yeah, free, easy 1 mark for you. Okay. All right. So now that's a relationship. Then next, how you are going to explain. Then how you are going to explain the graph. Okay. So normally we will explain 1. 1 is basically here to here. Then 2 is basically the optimum, and then 3 is from here to here. Okay, 1, 2, 3. So normally how we explain that, we will explain this point first, the optimum pH first. But for you, if you want to explain 1, 2, 3 also, never mind. But for me, I want to make it simple. I want to write the answer in the shortest sentence. So that's why I will explain this one first, 2 first. Okay, I will explain the optimum pH first. Then only I explain the 1 and 3 together. So that's why I no need to write that much. Okay. So how I explain that? Well, for 2, optimum pH. Okay. So the first part of the graph that I will explain is here. So I will explain the first thing. The rate of reaction will achieve the highest rate of the reaction at the optimum pH. That's the first one. Okay, achieve the highest rate of reaction at the optimum pH. That's the first one. Okay. Then next, the small changes or small deviation, okay, or when the pH change lower or higher than the optimum pH. You cannot say only lower or only higher. You cannot say like this. Okay, it needs to be lower or higher, okay, than the optimum pH. Then the rate of reaction will drop drastically, will decrease drastically. What's the reason? Why? Okay, why? So why? Well, you explain in terms of denaturation. So how you explain that? Yeah, how you explain that? Because the changes in the pH is going to denature the 3D arrangement, or it's going to denature the globular structure of the enzyme. That's the first one. Okay, why? Because the pH, changes in pH means what? Changes in pH means that changes in the concentration of the hydrogen ion. Changes in the concentration of the hydrogen ion is going to break the ionic bond and also hydrogen bond. It's going to disturb hydrogen bond and ionic bond. And these two bonding are the key bonding in the tertiary structure and also quaternary structure. So that's why the protein, the enzyme, will be denatured. Okay. So another thing. Besides that, changes in the pH will also affect the ionization of the active site. Changes in the pH will also affect the ionization of the active site. What it means by ionization of the active site? Well, just now we just mentioned an enzyme is a globular structure like this, right? Okay. So at the active site, their R group, their side chain will be all exposed like this, right? Waiting to form the bonding with the substrate. So when the substrate comes, they will be able to bind, right? Same shape, and then they can form the bonding with all of this. Okay? So these are side chain. These side chain, they can be acidic side chain. They can be the basic side chain. Okay? So acidic side chain, basic side chain. For example, this one, yeah. Let's say this one is a acidic side chain. It will have a COOH. At the optimum temperature, optimum pH, it should be what? It should be like this, COO negative, releasing the hydrogen. But now, if let's say you change the pH to become too acidic, when too acidic will means that in the environment there will be too many hydrogen ion. Too many hydrogen ion will actually inhibit the dissociation of this COOH. Then it will remain as COOH. It won't become COO negative, right? So when it not becoming COO negative, how is it going to form the bonding with the substrate? Cannot. It remains as COOH, nothing can happen. No bonding can be formed. When no bonding can be formed, then that means that the enzyme won't be able to recognize the substrate. So that means that the enzyme will fail to catalyze the reaction, and thus it will lower down the rate of reaction. That is the ionization of the active site. Same thing goes to the basic side chain. Basic side chain, which is NH4 positive, right? Supposed to be like this, okay? But for example, if let's say the pH become too basic means that the hydrogen ion become too low, right? Become too low, then they won't accept. They won't accept the another HAD. They will remain as NH3. Without the positive charge, how are they going to form the bonding? No. So that's why again it's the same thing. Okay. So that is the meaning of affecting the ionization of the active site. So because of these two, right, reason, so that's why changes in the pH will cause a very, very drastic drop in the rate of reaction. Because either way, the enzyme will not be able to catalyze the reaction at all. Okay, so that is for the graph of the pH. Yeah? So you can see that every pH, every enzyme, they will have their pH. Yeah, they will have their optimal pH. That's specific. Okay, but of course over here, the graph shouldn't be so fat. The graph should be, narrow a bit. Yeah, it should be narrow. Okay, that's the graph of the pH, and then lastly the temperature. Yeah, lastly temperature. Okay, so for the temperature, now what's the relationship? Okay, same thing. The relationship in the graph of temperature, right? There will be two parts. Before the optimum temperature, after the optimum temperature. Okay, so for the graph before the optimum temperature, the relationship is directly proportional. Before the optimum temperature, it is directly proportional, meaning that further increase in the temperature is going to increase the rate of reaction. Okay, so after the optimum temperature, well, means that, well, it will be a narrow, very narrow, right? A narrow change or narrow increase in the temperature is going to cause a drastic drop in the rate of reaction. That is their relationship. Different before and after, different relationship. Okay, so then next, how we explain the graph. Yeah, how we explain the graph. Yeah, so to explain the graph, will mainly based on kinetic energy. Okay, so three parts. Yeah. First part, before the optimum temperature. Second part, the optimum temperature. Third part, after the optimum temperature. Okay, so first part we will explain in terms of kinetic energy. Second part we will explain in terms of optimum temperature. Third part we will explain in terms of denaturation. Okay, so now let's see the first part. Before the optimum temperature, okay, normally same thing again. I won't say low temperature, high temperature. Okay, I will use the reference point as optimum temperature. Okay, because sometimes when the question change, they use, for example, let's say they use Taq polymerase. Taq polymerase, the optimum temperature is like 100 degrees Celsius. 100 degrees Celsius, then if you say at high temperature is denature, that's wrong anyway. Okay, so that's why I will say optimum temperature. Okay, so at the temperature before the optimum temperature, okay, further increase the temperature will increase the rate of reaction. Why? Right? Because when you increase the temperature, means that you are going to increase the kinetic energy of the substrate and the enzyme. Okay? So you increase the kinetic energy of the substrate and the enzyme, which means that the substrate and the enzyme will move faster. So there are higher chance for these enzyme and substrate to form the substrate-enzyme complex. Or you can say they will higher chance for the collision to occur also can. Higher chance for the substrate and enzyme, right, to collide each other. Okay, or you can say there are higher chance for the effective collision in between the enzyme and the substrate. Also can. There are many ways to explain that. Okay, basically, kinetic energy increase, temperature increase kinetic energy. Kinetic energy increase means that increase the chance of the effective collision. Okay, and with that, yes, that will increase the rate of reaction. Okay, so that's for the first part. All right, then next, second part. At the optimum temperature, at the optimum temperature, the rate of reaction will be at the maximum level. Okay, because why? Because this temperature is where most of the most effective for the effective collision to occur. Most effective for most of the collision to occur also can like this, something like that. Okay. Then after the optimum temperature, okay, further increase in the temperature will drastically decrease the rate of reaction. It will drastically decrease in the rate of reaction. Why? Okay. Because further increase the temperature after the optimum temperature is going to cause the denaturation of the enzyme. That's going to cause a denaturation of the enzyme. Okay, so that's why the rate of reaction will drop drastically. So if let's say the question want to further ask, why the higher temperature than the optimum temperature is going to cause the denaturation, and why the rate of reaction drops so fast? Yeah, why it drops so fast? Okay, why? Because enzyme is a protein, and that protein is very sensitive to the changes in the temperature after the optimum. Okay, why? Because there will be too high kinetic energy. Okay, and it's going to disturb the bonding. Yeah, it's going to disturb the bonding. Okay, so when the temperature is higher than optimum, so it's going to affect the hydrogen bonding. Okay, van der Waals forces, hydrophobic interaction. Okay, and even the ionic bonding. Okay, so and if you further increase, right, then it will break even the disulfide bridge. So all the bonding is almost affected. So that's why how is it going to survive that? So of course the enzyme will be denatured very fast. Okay, there will be a lot of the enzyme being denatured at the same time. So that's why after optimum temperature is very critical. That's very critical. Okay, so that's why you can see if you have fever, right, low fever, you also feel like very lifeless and you don't have energy. Why? Because the enzyme is very sensitive. You increase a bit, they are not so working well already. Okay, so that's why the rate of the ATP production will be dropped. So that's why you will not just ATP, glucose also. So that's why you will start to feel like lesser energy, and you don't have the appetite also because the enzyme, all the digestive enzyme is not working well. Okay, so that's why anyone have experienced high fever before and then enter a hospital? Yes. So what the doctors and nurses will do to you at the first point? Ice bucket challenge. Like they will dump you into the ice bathtub. A bathtub that's full with ice. They will dump you in. Okay. So normally, when achieving 39 degrees Celsius, yes, they have to be 39 degrees Celsius is quite critical already. Okay, because once it achieves 40, 41 degrees Celsius, you will become retarded. Irreversible. Yeah, it's irreversible. So once 41 degrees Celsius retarded, then so that's why if you reach hospital 39 point something to 40 degrees Celsius, right, they will directly want to dump you into the ice, right, the ice tub. Why? Because to cool you down immediately. There's no other choice already. Okay? If let's say you still don't want to cool down, 41, 42, that's what happens. So it's not play on this side. Okay. All right. So then next part 4, we'll look at the enzyme cofactor. Yeah. Okay. Enzyme cofactor. There are 3 enzyme cofactors that we will look at. Okay, enzyme activator, coenzyme, and prostatic group. Okay, three cofactor. Yeah. So what is this cofactor? Well, for some of the enzyme, right, they will need to bind to something else. Then only then it will become fully functional. If they don't bind, then well, they are just inactive. Yeah, they will just remain inactive. Okay, so that's something that the enzyme that must bind in order to become fully active is the so-called cofactor. That is the so-called cofactor. Okay. So this cofactor, yep, as you can see here, the enzyme, okay, need to bind to the cofactor, then only they become fully active. Then only then they are ready to catalyze the reaction. Okay, so the enzyme that is not binding to anything that is not active, we call it apoenzyme. Apoenzyme. So after they bind to cofactor, then they become fully active, then they are so-called holoenzyme. Okay, so that's the name for the enzyme, fully active or not active. Okay. So there are three types of the cofactor. There are three types of the cofactor. Okay. Some of it will bind temporarily, some of it will bind permanently, some of it will bind to the active site, some of it will bind to some other site. All right. So that's why this is the key that you need to put down. Yeah. And I have put down in the mind map. Yeah. So you can refer to the mind map later. Okay. So that's the important point that you need to know. So there are three types. Yeah. So first one is the enzyme activator. Enzyme activator are normally metal ion. Normally, most of them are metal ion, but of course there are some other ion also. Okay. So now the enzyme activator, they are non-protein. Yeah. Enzyme, the apoenzyme is the protein. Okay. Then they bind with this enzyme activator. This enzyme activator is a non-protein inorganic molecule. Non-protein inorganic molecule. Okay. So normally, most of the time, yeah, they are ion. Most of the time they are ion. Okay, for in our body, right, most of the enzyme, most of the enzyme that need the enzyme activator, right, the enzyme activator that they need is ion. So that's why in our diet we will need mineral ion. You see the mineral ion like the calcium, zinc, magnesium, iron, chloride ion. So all of this, right, all of these, they are basically the mineral ion that is needed in the diet. Okay. So what are the examples? Well, this example, yeah, those examples that's given in the note, yeah, maybe you will need to know that, yeah. Okay. So the example given here is thrombokinase, yeah, thrombokinase. Okay. So thrombokinase is the enzyme, right, in your blood, right, in the blood. Okay. They will need calcium ion as their cofactor. Okay, they will need that because without the calcium ion, means that it cannot stop the breathing. Yeah? Because this thrombokinase, is important to change the prothrombin to become the thrombin. Well, when you breathe, right, it will be blood clot. Normally, in 3 minutes time, the blood should clot and stop. Whenever you accidentally cut yourself, okay, it should stop the breathing within 3 minutes. If let's say, in 3 minutes time, the blood still flushing out, all right, then that means that you have some problem with your blood clotting mechanism. Then you need to check in the hospital. Okay, unless if you cut the artery, that's a different story, lah. Okay, cut artery, that one won't stop one. Yeah? Okay, that one we will discuss in the STEM 2, right, in Bio 2. Okay, cardiovascular system. Okay, so this one is let's say you accidentally cut any vein, the blood should stop within 3 minutes. Okay, so if let's say it's a big cut also, it's a very big cut also, let's say, you just have to put direct pressure like this. It will stop. It should stop within 3 minutes. Okay, so why? Because the enzyme. Okay, the enzyme, yeah. The thrombokinase, well, this one I think you have learned in secondary school. It's just that I'm not sure whether you still remember or not. Okay. The prothrombin, which is a protein inside your blood, yeah, in your plasma. Okay, the prothrombin, it will be converted to become the thrombin. This is where the thrombokinase act on. the enzyme thrombokinase. Okay, so the thrombin later is going to cause the fibrinogen, which is another protein inside your plasma, okay, which is soluble, to become fibrin. Fibrin is actually a long strand that's insoluble. So when it become like this, right? So let's say this is the blood vessel, a break in the blood vessel, right? Okay. So what will happen is that these fibrin, when once they are formed, they will form a web like this. So now the red blood cell cannot go out. The red blood cell will stick here, will clot, will form a clot. Okay, so that is the fibrin. Okay, so some people, they don't have enough calcium. Okay, so especially when your diet, yeah, you didn't drink milk, you didn't like to eat those green vegetable, this is when that will happen. Okay, so if let's say you don't have enough calcium, means what? Means that the calcium, okay, it is needed in order to activate the thrombokinase. Then thrombokinase will change the prothrombin to become the thrombin. Thrombin change the fibrinogen to become the fibrin. That only then blood clot occurs. If you don't have enough calcium, means that thrombokinase won't work. Thrombokinase won't work. Prothrombin will still be changed to become thrombin, but then it will be super slow. Because without enzyme, everything is like super slow. Okay, so you will still keep on breathing for hours. Yeah. Okay, so that's why the enzyme is so important. Okay, so this is the one of the example. Okay, that can help you to memorize that. Okay. Then next we look at the coenzyme. Then we look at the coenzyme. Okay. So for coenzyme is non-protein organic. Non-protein organic. Yeah. Okay. Yeah. So I forget to talk about this. The metal ion, the enzyme activator, right? Enzyme activator, they will bind temporarily to any site of the enzyme. They will bind to any site of the enzyme, not the active site. Yeah? So it's basically like this. For example, at the beginning, this is the active site. This is how it looks like. Okay. So the activator, right? The activator needs to bind to any site of the enzyme so that they make the changes to the active site. Okay. So when they make the changes to the active site, now only then the active site can fit in the substrate. Okay. So that's how the enzyme activator actually works. Okay, so they bind loosely, they bind temporarily only. Okay, and then they will bind to other site, any other site of the enzyme. Okay, then they change the shape of the active site in order to make the enzyme more suitable to fit in the substrate. Okay, then next is coenzyme. Coenzyme, they will bind temporarily as well. They will bind temporarily, but then they bind to active site. Yeah? They bind to active site. Okay. So how they work? Well, they bind the active site so that they can help to transfer the molecule or ion or electron. Okay. So that's how it works. They help to transfer the molecule, atoms, or ion or electron. Okay, because when you have reactant and reactant want to work, right? Okay, enzymes don't involve in the reaction directly, right? Okay, so let's say the reactant, in order to form the product, right, they need to transfer the electron, or they need to transport transfer the atoms or all this. Okay, then who is going to transfer that? Coenzyme is going to transfer that. Okay, so that's their mechanism. Okay. So how they work? Yeah, how they work? Well, one of the example that we always use is this one, the coenzyme that derived from the vitamin B, okay, which is the nicotinamide adenine dinucleotide, NAD. NAD. Yeah, NAD is actually derived from the niacin, which is vitamin B3. Okay, so this NAD, right, is actually a very important coenzyme for this dehydrogenase. Yeah, for dehydrogenase. some real life example that you can actually feel it. Alcohol dehydrogenase. Okay, alcohol dehydrogenase. Okay, so alcohol dehydrogenase is basically the enzyme that is important to break down the alcohol, break down the ethanol. Okay, so when you drink, when you drink, you can see some people, they drink a bit, their red, their face will be so red, and then some people they will get drunk easily. But some people when they drink, they can drink like whole gallon and then nothing. How come? Well, this one is actually genetically derived. Okay, so it depends on how much dehydrogenase you can form. Okay, so well, I have a friend who actually not just one friend. I have a few friends who work as a service engineer. Okay, so as service engineer, they sell the machine, and then they need to service the customer, right? Okay, so one of my friends, he actually served the Russian company, right? So Russian, they drink vodka like drinking water, all right? Nothing to them basically. It's like nothing to them. They can keep on drinking. So that's why when they come to Malaysia, right? Then when they meet my friend, right? My friend need to serve them, entertain them. Okay, so need to bring them to the club and then drink. Okay, but the thing is, Russian genetically they have much higher dehydrogenase, alcohol dehydrogenase compared to Chinese. Okay, Chinese, well, basically our genetic, right, is having very low dehydrogenase. So that's why for Chinese, well, you cannot compete at all. You try to compete, well, genetically they win on you. Genetically, well, you can't compete with them. They can drink vodka like nothing, whole night for the whole night. Okay, so what happened is that my friend is basically party all night, and then after that, hangover. Basically, this is what happened. This is what happened to him. So that day when I have just asked him to go out for a basketball game. But then when I reached his home, he's like going to die already. So I asked him, "Bro, what happened to you?" So he tell me, "Cannot, I will die. If I keep on doing this job, I will die one day." Then I asked him why. Then he said, "Yes, he's having hangover." So yeah. So I say, "Yeah, you know why? Because you are an engineer, you didn't study bio. So if you study bio, you can save yourself." So this is what I teach them. Actually, got two tips. One more tip is related to digestive system. This one we'll discuss during the STEM 2. Okay. So enzyme-wise, the first tip enzyme-wise is yes, take vitamin B. Yeah, take vitamin B complex. B complex, not just B3. B3 is because for alcohol dehydrogenase. Okay, but you still need B6 and B12. Okay, in order to reduce the hangover. Okay, but for B3. It is important. Why? Because, well, why you are drunk? Yeah, why you are drunk is because alcohol is basically CH3, CH2, OH. That's alcohol. Ethanol. All the alcohol that you can drink, right, is ethanol. You cannot drink methanol or propanol, you'll be dead. Yeah. Okay. So basically, what an enzyme do? The enzyme basically come here. Their active site, right? Okay. Their active site, they will need something to transfer. So alcohol dehydrogenase is mainly breaking down the alcohol to become acetaldehyde. They need to break it to become what? Break it to become CH3. Okay, C double bond OH. They need to break it to become acetaldehyde. Okay, so once you break it down, then you won't get drunk. So that's why you have to you have to increase the speed of this enzyme, of this alcohol dehydrogenase to break down. Okay, so in order to speed out the alcohol dehydrogenase to break down the alcohol, well, you learn that because dehydrogenase will need the coenzyme, and the coenzyme is actually the NAD. NAD is from your B3. Okay, so that's why when you have the niacin, let's say, okay, so it will form the coenzyme here. So the NAD will be the coenzyme here. So if you still remember how the coenzyme works, coenzyme will transfer. Coenzyme will help to transfer. Okay. So in this case, dehydrogenase is basically going to transfer the 2 hydrogen. They will transfer the 2 hydrogen so that this one will become the acetaldehyde. Okay, so it transferred to become NADH plus H plus. So that's why. Okay, so you can see that this is how the NAD actually works. That's how the coenzyme actually works. So once they transfer, you can see the NAD detach. You see that? NAD now become NADH and H plus. So it detached. So that's how it transfers. So once you transfer out, then yep, it will become acetaldehyde. Okay, you get it? So that's how the whole enzyme actually works. They transfer the molecule. Enzyme don't involve at all. You can see that they don't involve. Okay, it is the NAD, the coenzyme that work on it. Okay, get it? So this is how the coenzyme works. So same thing back to this. Well, alcohol, it will break down to become acetaldehyde. Yeah. So how come some people after they drink they will be red? Because acetaldehyde is also toxic to you also. You will become red is because accumulation of acetaldehyde in your blood. So that's why you become red. Okay. So to break down this acetaldehyde, you need another dehydrogenase. Right? You need acetaldehyde dehydrogenase to further break this to become the acetate and acetyl-CoA, which is less toxic. This one you will learn in the cellular respiration. Yeah. So that's why, yeah, if let's say if you drink a bit of alcohol and then your face will turn red, right? My advice is you better don't drink. Okay, why? Because genetically you are lacking of the acetaldehyde dehydrogenase as well. So that will mean what, you know? That will mean that acetaldehyde will accumulate in your blood easily. And acetaldehyde is toxic and carcinogenic. You are having 10-fold higher chance to get the liver cancer. So that's why you better don't drink. If let's say after you drink, your face won't turn red, then that means that genetically you are gifted. You have more dehydrogenase, you have more NAD that can actually break down it very fast. That one, yes. Okay, all right, so that's the example, yeah? All right, then next we'll talk about the prostatic group. Okay, next one, prostatic group. Prostatic group, they will bind permanently. They will bind permanently, yeah? Permanently to any site of the enzyme, to other side of the enzyme. Not the active site, just any site of the enzyme. It depends on what type of enzyme is that. Okay? So prostatic group is directly involved in the catalytic function itself. It directly involved. So that's why it's always there. Okay? So the example, well, hemoglobin, myoglobin. Hemoglobin, myoglobin, they will have the heme group as their prostatic group. Because with that, it can catalyze the reaction where the oxygen binds to the hemoglobin. Okay? But maybe this is not a very good example. Another example that, using the heme group, using the heme group as this prostatic group would be the catalase. Well, catalase, do you know catalase? Catalase is the enzyme that, it's the enzyme that enables us to survive now, right now. Why? Because oxygen is toxic. Yeah. When you breathe in the oxygen, now oxygen is going to kill you actually. But then why you didn't die? Because we have a lot of catalase. Every single cell in us that's exposed to the oxygen, they will have the catalase. In fact, oxygen, when you breathe in, right? Oxygen, when you breathe in, it will become the what we call ROS, reactive oxygen species. One of the examples is hydrogen peroxide. Well, we know that it is going to kill yourself, hydrogen peroxide. Okay, but why you don't die? Because the hydrogen peroxide will be immediately, it will be immediately break down to become water, okay, and also the oxygen. Okay, so that's why you don't die. Okay, so how the catalyst can react so fast? Because they have the heme group. Yeah, because they have the heme group. Okay, so whenever there's a reactive oxygen species come in, they can just react on that. So that's why it's bind permanently. It's no longer like, it's no longer like, okay, bind and attach, detach, bind, detach. No. Heme group, they always bind on the catalyst. So whenever there's a ROS, they will break it down. Okay, there are so many ROS, not just the hydrogen peroxide. Okay, so maybe this is one of the reasons why we are still not conquered by the alien. And that might be the reason, because the alien, where they never exposed to oxygen, they come into our Earth, they will be killed. For sure, they will be killed. Okay, maybe, who knows? Okay, all right. So that would be the prosthetic group. All right. Then lastly, inhibitor. Okay, so for enzyme inhibitor, enzyme inhibitor is basically anything that is going to inhibit the reaction or slow down the reaction, either one. Either directly inhibit the reaction or slow down the reaction. That one is all considered as inhibitor. Okay? So the inhibition, they can be reversible, they can be irreversible. As I said, it depends. It depends how the inhibitor binds to it. Don't worry, it's not a COVID. Because I am having the tonsillitis. COVID is not going to cause the tonsillitis. Okay, so depends on how they bind. Yeah, depends on how they bind. Yeah, okay. They will be reversible or irreversible. Okay. Either they bind temporarily or they bind permanently. Okay. Then based on based on their mechanism of action, we can categorize them as competitive or non-competitive. Okay, so let's see. Yeah, let's see what it means by competitive. Okay, competitive inhibitor. Competitive inhibitor, first thing, they have similar structure with the substrate. Competitive inhibitor will have almost similar structure like the substrate. Okay, why? Because so that they can bind to the active site. So that's why competitive inhibitor will bind to the active site. Okay. So in other words, you see, their name is called competitive inhibitor. In other words, means what? Means that they will compete with the substrate for the active site. They will compete with that. Okay. So because of this, when they compete with the substrate for the active site, okay, if they say they win, right, they bind to the active site, right, then nothing happens. They won't produce a product. Okay, so it's basically to do what? It's basically to decrease the chance for the substrate to bind to the active site only. Okay, because if without the inhibitor, without the competitive inhibitor, okay, basically substrate and the enzyme, right, whenever they hit each other, means they bind. This 100% of chance they will bind, right? But then with, let's say, with the competitive inhibitor, now you have one enzyme, okay, but you have one enzyme and one inhibitor. So the chance for this substrate to bind to the enzyme is now 50% only. You lower the chance. You lower the chance for the substrate to bind to the enzyme because they will compete. Okay, so it's 50% of chance because it's random motion, right? Whenever you add another the inhibitor, there are 50% of the chance the inhibitor will bind. If inhibitor bind, that means nothing happened. You are wasting the chance. You wasting the chance means you lower down the rate of reaction. Because when inhibitor bind to the enzyme, nothing will happen. They will not produce the product. Okay, get it? So that's how it works. Okay, they will compete for the active site. Okay, but this effect of the inhibition, right? Inhibition by the competitive inhibitor can be reduced by increasing the substrate concentration. Okay, and eventually back to the maximum, rate of reaction. Okay, how? How come increase the substrate concentration can reverse the inhibition by this competitive inhibitor? Well, it's all by chance, right? Yeah, it's all by chance. Okay, so for example, yeah, now I have enzyme. Let's say I have 4 enzymes, let's say. Okay. So I have this one is the substrate 4, 5, 6, 7, 8. Okay. So at the very beginning, yeah, okay, without any inhibitor, what is the maximum rate of reaction? Let's say one enzyme can catalyze one substrate in 1 second. Okay. So what is the maximum rate? Maximum rate is product per time, right? Okay. The rate of reaction is product per time. Okay. So one can bind here, one can bind here, one can bind here, one can bind here. Maximum 4 products can be produced 1 second, right? So what is the rate of reaction? 4 over second, 4 per second. Okay. So now I add the inhibitor. 3, 4, 5, 6, 7, 8. So when you add the inhibitor, what is the chance for this substrate to bind to this enzyme? 50%. Okay. So that means that maybe this one will bind here, but this one maybe the inhibitor get in. This one maybe the substrate go in. This one maybe the inhibitor go in. Okay. So what is the rate of reaction now? 2 per second. Because only 2 substrate able to bind. Another 2 is bind by the inhibitor. So now the rate of reaction dropped to 2 per second. Right? So that is the effect of the inhibition. So now how are you going to reverse the effect of this inhibition? You can increase the substrate concentration. How are you going to increase that? Well, you can add more. So when you add more like this, what is the chance? Okay, it will be higher chance now, right? Okay, so maybe this one will bind, okay? Then this one will bind here, this one will bind here, this one will bind here. Because when you have more substrate, there are more chance for the substrate to bind to the enzyme. Okay, so with that, what is the rate of reaction now? You increase back the rate of reaction back to 3 per second now. So if you further increase the substrate, there will be higher chance that in the end, it will back to 4 per second. Right? It will back to the maximum rate of reaction again. Okay, so that is the concept. Yeah, that's the concept of this competitive inhibitor. Okay, so that's the mechanism. As you can see here, they will compete. Yeah, they will compete for the active site. Yeah, they will compete for active site so that they block the substrate. They don't allow the substrate to bind to the active site. Okay, but they are binding temporarily only. They are binding temporarily, so that's why later they will detach also. Okay. So now we look at the graph. Yeah, we look at the graph. Okay. So to interpret the graph, this is a combined graph. Yeah, this is a combined graph. Okay. But as for now, we look at the green line, which is uninhibited, and also the blue line, which is competitive inhibitor, adding with the competitive inhibitor. This is the reaction without any inhibitor. This is the reaction with the competitive inhibitor. Okay. Okay. So now, first thing first, how are we going to analyze this graph? Or how are we going to identify this graph? Okay. We only look at 2 keys. Yeah, we only look at 2 keys. Okay. Well, one is we look at the Vmax. Vmax, yeah. Vmax will mean that the maximum velocity. Vmax, maximum velocity. In other words, the maximum rate of reaction that this reaction can achieve. That is the Vmax. Okay, so based on the Vmax, you can have the half Vmax. That means that half of this, 50% of the Vmax. Okay, so that is the key. Yeah? Vmax, that's the first one. Okay. Second thing that we look at is the Km. Km. Okay. Km, if you want to search, right, this Km is not kilometer, please. Okay, this M is a smaller one, yeah, a subscript one, okay. This one is actually a Michaelis-Menten kinetic. Michaelis-Menten kinetic. In exam, you want to write this Michaelis-Menten kinetic, or you just want to write Km? Okay, then Km. Okay, we make it simple, Km. Okay, so I will accept Km then. Okay, so now what is a Km? Yeah, what is a Km? Km actually means that what is the substrate concentration that is needed in order to achieve half Vmax. What is the substrate concentration that is needed to achieve half of the Vmax? That is the Km means. Okay. In other words, Km actually means what? You know, Km actually means the affinity for the enzyme to bind with the substrate. Because when the Km is lower, means that the enzyme is having higher affinity to bind to the substrate. In other words, the chances for the enzyme to bind with the substrate will be higher. Get it? All right. So that's why higher Km means that the chances for the enzyme to bind to the substrate is lower. So that's why the affinity is lower as well. Okay, so I review it again, yeah, slowly. Okay, don't worry. For the Km, okay, you see that Km is determined by how much substrate concentration is needed in order to achieve the half Vmax. Okay, it also means the affinity of the enzyme to the substrate. Okay, higher affinity means what? Means that higher chance to bind. Lower affinity means lower chance to bind, right? Okay. So now, when you have low Km, the enzyme having low Km means that low Km means what? Means that they only need lower substrate concentration to achieve that velocity, to achieve that rate of reaction. How come you will need lower concentration of the substrate to achieve that same rate of reaction? Because your affinity is higher, what? The chances to bind to the substrate is higher. So that's why you don't need that much of substrate. You just need maybe 5. You can actually reach the edge because the affinity is higher. The chances to bind is higher, so you don't need that much of the substrate concentration. Lower substrate concentration also, never mind, you have higher chance to bind. So that's why you can still achieve high rate of reaction. So that's why low Km, high affinity, higher chance to bind. High Km means that you need higher substrate concentration, right? Okay, higher substrate concentration. Why you need higher substrate concentration in order to achieve that rate of reaction, that same rate of reaction? Because affinity is lower. Because the affinity is lower means the chances is lower. Okay, if let's say you remain as 5, the chances is lower, you will miss it. So that's why you now need 10. You need more substrate. Then only then with the lower chance, only then you can meet that. Then only then you can achieve the same rate of reaction. Okay, get it? So that's why lower Km means higher affinity, means higher chance. Okay, higher Km means that lower affinity, lower chance. Okay, so that's how you read that. That's how you analyze the graph, and that's the meaning behind this Vmax and also the Km. Okay, so now, Danya, you understand the basic concept of this Km and Vmax already, right? Okay, so next will be very simple already. Okay, next will be very simple. Okay, compared to the uninhibited one, and competitive inhibitor, is it going to change the Vmax? You see the blue line, is it still reaching the same Vmax? Yes, so that means that competitive inhibitor will not change the Vmax of the reaction. It will not change the Vmax of the reaction. Okay, same Vmax. Okay, but you look at the Km. You see the blue line and the green line, yeah? Because they are having the same Vmax, right? So that means that their half Vmax is the same. Okay, their half Vmax is at this point. Okay, for the green line uninhibited one, what is their Km? Lower, you see that? Okay, for the blue line with the competitive inhibitor, what is their Km? You see higher. All right, so that means what? That means that it has increased the Km. You see that? It has increased the Km. Okay? So that means that competitive inhibitor is going to increase the Km, but got no effect on the Vmax. This is the key. And it has been actually jotted down in the mind map, yeah? So don't worry. Yeah, you can see here. Competitive inhibitor is going to increase the Km, but remain the same Vmax. That is the key for you that you need to remember. Okay? Then next, we look at non-competitive inhibitor. Non-competitive inhibitor is not like the competitive inhibitor. Yeah? Non-competitive, you see the name, non-competitive means that they don't compete at all. Yeah, they don't compete at all. Yeah, okay. So they don't have structural similarity. They are not same. They are not same like not like the substrate. Not same at all. Okay. They don't bind to the active site. They will bind to allostatic site. They will bind to allostatic site. Okay. So how they work? Basically, this is the active site, right? Allostatic site will be somewhere other, right? Some other site. All right. That's allostatic site. It's a very specific site. Allostatic site. So the non-competitive inhibitor, they will come and bind to the allostatic site. When they bind to the allostatic site, what will happen is that they will cause the conformational change of this enzyme. And this one, right, is going to cause a very big change. It's going to cause a very big change. So when it causes a very big change, they will shut down the protein. They will shut down the enzyme. The active site will no longer functional. The active site will be no longer functional. That means that no other substrate can bind anymore. It's not like the competitive one. Competitive one, they will compete, they will bind to the active site, then they detach. They bind and detach. They just try to block only. They bind and detach. Okay? So that's why other substrate can still bind after that. After they detach, they can still bind. But this one, non-competitive, they will bind to the allostatic site, they shut down. They shut down the enzyme. So the enzyme is totally wasted. Okay? So that is how the non-competitive inhibitor actually works. Okay? So normally they will bind permanently. Normally they will bind permanently. So that's why it cannot be reversed. Okay? But some of these non-competitive inhibitor, they can bind loosely. If they bind loosely, they detach, and then the enzyme will reverse. Okay? But then most of the time they won't reverse. They will bind permanently. Okay? So this is how it works. All right? So now look at the graph. Now look at the graph. You have no Vmax and the Km. Okay? By looking at the graph, you see the non-competitive inhibitor, which is orange line. Okay? You see that they are lower. The Vmax will be now lower. Okay? The Vmax will be now lower than the green line one. You see that? Okay? Why? Because non-competitive inhibitor is going to shut down the enzyme. So that's why it's going to lower down the maximum velocity. It's going to lower down the maximum rate of reaction. Why? Because you have, let's say, initially 4 enzymes, right? Okay. So with your substrate, yeah, happily you can achieve 4 per second. All right. Now, you add the non-competitive inhibitor, you shut down. These 2 enzymes is no longer working. Okay. So what is your maximum rate of reaction now? It can be only 2 per second only. That's the maximum. Okay. You further increase the substrate. Is it useful? No, because the enzyme itself that is available is now only 2 only. No matter how much substrate you increase, it won't be reversed. Okay, get it? So that's why that is the difference between non-competitive and also the competitive inhibitor. Okay, so based on the graph, they will reduce the Vmax. They will decrease the Vmax. Okay, but Km will remain the same because when you reduce the the Vmax, right? Where is the half Vmax for this graph? Half Vmax will be here. Okay, half Vmax will be here. So is the Km for this half Vmax same with this Km? It's still the same. Right? So that's why the Km is still the same. Okay, so what you need to remember here, non-competitive inhibitor, they will remain the same Km, but it's going to lower down the Vmax. All right, So there are actually further explanation on how and why the Km is not a factor, why the Vmax is a factor, blah, blah, blah. There's a lot of explanation on that, okay? It's just that it is not in our syllabus. Yeah, it's not in our syllabus, okay? But A-level study that, okay? Your competitor, they study that, okay? They study in more detail. For us, no. For us, you only need to know this and this and that. That's it. You don't need to know how to explain that, okay? But for your competitor who are studying IB, STPM, and also A-level, they are studying it, okay? So if let's say you are interested to know, to study further, okay? If you want, you can study the A-level books, okay? Or if not, you can also search for my video as well, okay? I have a video for that, okay? All right, then after that, just very last part, yeah, done with this. This is a summary, yeah. Okay, this is a summary. It's the same thing, yeah, it's the same thing, the summary, okay? So lastly, reversible inhibition. Reversible inhibition, all the competitive inhibitors are reversible. All the competitive ones are reversible, okay? Well, some of the non-competitive inhibitor can be reversible as well. It can be reversible. It depends on whether they bind temporarily or loosely, right? Or permanently. If permanently, then it will be irreversible. But if let's say they only bind temporarily, then it will be reversible. Okay, get it? That's why I am stating here, right? You can see here. It can be irreversible, it can be reversible, okay? Well, for irreversible inhibition will means that it's normally non-competitive only. Competitive, no. Only non-competitive. And this non-competitive inhibitor will bind permanently. They will bind permanently, meaning that they will bind to the allosteric site normally with the covalent bonding. When they are using covalent bonding, normally it will bind permanently, then you cannot break it already. You cannot break it means that they will destroy the enzyme activity at all. So that's why it's irreversible. Okay? So what are the irreversible example? What is the example of the irreversible inhibition, right? Example, nerve gas. Okay? During World War I, this one, you see there will be gas bomb, gas grenade. Okay, so that's why during that time they are all wearing the mask. They have to wearing the mask, okay? And not just the soldier, okay? Because if the soldier, if let's say you didn't wear the mask, well, nerve gas is attacking the enzyme, right, for your neuron, acetylcholine esterase. So that means that it will stop the neuron transmission. Stop the neuron transmission, your diaphragm cannot work. When your diaphragm cannot work, so that's why you suffocate, you will die, okay? Or you will blind sometime, okay? So that's why you need to wear the mask. And actually, not just the soldier, yeah, all the horse, war dog, they all wear the mask. And during that time, one of the hot items is this one, baby mask also. Yeah, because the enemy will not just release the gas bomb in the war zone. They will release at your home also. Okay, so that's why. That's one of the hot items. Okay, then maybe you will say World War I is too far from you. Then there's one that is very close to you. You know him? Yeah. Yeah. Okay, Ahsoka. So this is one of the founder of the Japanese cult. Yeah, he claimed that he is a prophet. Yeah, but then of course he's not. He's just bullshit. Okay, so he claimed that I forget what year is that already. I think 1996 or 1990. I forget the year already. Okay, so during that year he claimed that there will be a disaster in the Tokyo. Then of course he's not a prophet, right? So in order to make himself a prophet, he asked his follower to release the sarin gas, so that it become a disaster. So this one is but this is a Japanese count. Yeah, so the styrene gas that is being released is also the same thing. It's also one of the irreducible inhibitor as well for the acetylcholinesterase as well. Okay. Then one last thing is about this end product inhibition. Yeah, end product inhibition. This is application in our body. How we control the reaction, because all the reaction is by enzyme, right? For example, your body want to produce the amino acid threonine to become isoleucine. Example, glucose. Okay. Once the cell take in the glucose, it will undergo glycolysis, break it down to become the GGP and also the ATP. They want to produce the ATP. Okay. But our body don't need that much of ATP, especially when you are sleeping. Okay. So how the body control that? How the body want to stop the enzyme? Because enzyme is there, it's always working. Okay. So how to stop that is basically like this: end product inhibition. For example, you have the glucose, yeah? This one is, let's say, glucose. So your enzyme 1 will work on it, break the glucose, then go through the glycolysis, and it become the end product. Okay? Then this end product will be used to form the ATP in the Krebs cycle later. Okay? So if, let's say, you don't need that much of ATP, when you don't need that much of ATP, then that means that it will stop here, right? So there will be accumulation of this end product. And this end product, when it accumulates, it will go and inhibit the enzyme 1. It will stop the glucose breakdown. So with that, it slows down the whole reaction. So that's how your body actually controls the reaction, the pace of the reaction. Okay, so later when you wake up already, you start to use up all of this to make the ATP. No more end product, then the inhibition gone. Then when inhibition gone, then the enzyme 1 will work again. So normally, the end product inhibition, they are using the either competitive or non-competitive inhibition in order to stop or let go of the reaction. So that's how it controls the pace. Right? That's the so-called end product inhibition. That's how the competitive inhibitor or non-competitive inhibitor is being applied in your body. Okay, get it? Right, so basically that's it. That's all for the lecture today. Right, so thank you everyone. For the next class, we will be looking into the tutorial then. Okay, so try to finish the tutorial for this enzyme as well, yeah? Okay, so we try to finish 2 tutorials in the next class. Okay, so see you all.